So I will talk about time-delayed cosmography, and as Christian already said, there is some tension developing in measuring the expansion rate of the universe, the Hubble constant, from precision cosmology. Up to a few years ago, as I will show in a moment, there was not much tension because the error bars on various methods and the values from various methods were still so large that the errors were overlapping. Nowadays, cosmology is so precise, but maybe not so accurate, in a way that some tensions are now developing between various measurements of the Hubble constant. And in particular, if one measured them with probes in the early universe, being the cosmic microwave background, and also baryonic acoustic oscillations, sort of the same physics, and what are called late universe measurements, such as supernovae, but also, as I will show today, gravitational lensing. So let me switch to the next slide. Right, I'll go and introduce very quickly, for those maybe not so familiar, right, the success of the standard cosmological model. So we all probably have heard of the standard cosmological model, right? It's a flat universe, it has dark energy, it has dark matter, and it can be described very well by 6 free parameters, and it can actually describe the universe, at least on large scales, extremely well. So it's been a great success over the last 2 decades. But slowly now, the measurements of these parameters from various methods start to sort of diverge. And this is not just the Hubble constant, but that's what I will talk about today. There are also tensions in other values of these parameters, although they're all in some sense coupled. The largest tension developing is that in the value of the Hubble constant. So some cracks are appearing in this model, right? And this model is, of course, largely based on the cosmic microwave background, right? We see a picture of the Planck collaboration here. And from these fluctuations of the cosmic microwave background, one can measure a power spectrum like this. And by fitting models to this power spectrum, this is relatively well understood physics, one can constrain combinations of the various parameters that I have just shown, of those 6 lambda CDM parameters. And they are extremely accurately determined, although there are clear degeneracies also in the cosmic microwave background. So if one, for example, makes the assumption that the universe is flat, then many of those degeneracies in the CMB models can be broken, and one comes up with pretty well-determined parameters. On the other hand, in the more nearby universe, one has, for example, distance measures from supernovae. Now, they're often calibrated on other methods, but in principle, one can measure the expansion of the universe, the expansion rate, and also the combination of cosmological parameters from supernova out to redshift beyond 1. So in the very nearby universe, you just measure the expansion rate, but if you measure further out, you can also measure the acceleration or deceleration of the universe. And this, of course, led to the Nobel Prize for showing that the universe is accelerating and not decelerating. So there is some other form of dark energy that makes the universe accelerate. Right? So also the supernova measurements have a measurement, they have information in them that allows us to measure a combination of the expansion rate and the other cosmological parameters. Now, if you put this all together into a very well-known plot, of course, of, for example, omega matter versus dark energy, then you see that none of these methods is really breaking all the degeneracies, but they are having different degeneracies. For example, the supernova or measurements of clusters. From clusters, you measure much more the total mass content of the universe. and then of the CMB. If you combine them all, right, you find that, let's say, sweet spot where the red circle is drawn for a universe that is has some component of matter, dark matter, and baryons, and some component of dark energy, maybe a cosmological constant. And the universe on that black line there, that diagonal black line, is flat. So this model, the standard lambda CDM model, suggests the universe is flat. There is some dark matter, there's some dark energy, maybe cosmological constant, and that seems to work extremely well. We have to keep in mind, of course, that dark matter and dark energy are both components that we have given a name but don't really understand. Now, if you take those CMB fluctuations, they have a power spectrum. You can also predict more or less structure formation in this scenario, right? And large scale right, the formation of clusters of galaxies. So this has been an extremely successful model, at least if you sort of disregard anything on scales much smaller than a megaparsec. Anything on large scales in the universe seems to fit this model. So I will just skip that. So what I will focus on today, right, is on cracks appearing in this model. This model seems very successful on many scales. One can measure those 6 parameters extremely accurately, but right, or let's say not accurately but precise. But the accuracy now is where the problems are starting. So today I will focus on the Hubble constant because this is one of the best, let's say, examples of this tension appearing. They're also appearing in measurements of, for example, sigma 8 or combination of sigma 8 and omega matter, but those tensions are still weaker than the ones in the Hubble constant. Right, so the Hubble constant is, in some sense, the expansion rate of the universe at this moment. But if you look at the expansion of the universe, right, obviously it depends on its energy density. Right, it depends on omega matter, it depends on omega lambda, maybe on the equation of state, and maybe some other things as well. So there is an expansion history to the universe. So if you are measuring the Hubble constant, H0, then, but you're measuring them, right, with probes at high redshift or intermediate redshifts, in some sense, you have to know what that expansion h of z with redshift has done in order to infer H0, right? So many of these methods, like the CMB, they don't measure the Hubble constant directly. They measure it by having a model for the expansion function of the universe. Now, of course, H0 is very important. It sets the age of the universe, or you can determine the age of the universe from it, right? The physical scales of objects, the energy budget, right? So there's no question that this is a very important parameter. So what is the current status of measuring H0, right? So, so first of all, I think, of course, there has been a lot of work on this, and maybe up to the maybe 2000, the year 2000, there was this sort of dichotomy, right? Could it be 50 kilometers per second per megaparsec or 100 kilometers per megaparsec? And that sort of question lingered around for almost 50 years until that seemed to be settled around 2000 by the Hubble key project, and they were settling on somewhere around 70 or a little bit more. Now, of course, this was expanded to higher and higher redshifts at supernova, and that is what's shown here. If you look at the error budgets, for example, on the HST key project in 2001, right, one has errors of order few percent up to 5% of many of the steps that go into that measurement. But as time progresses, these methods and the way they are calibrated, the data became better. And now in 2020, 2019 here, the last part in the left diagram, you see that the errors on each of those steps is almost 1% or much less than that. So if you quadratically add these errors, you might get to a precision of 1 to 2%. So that's sort of the precision one is thinking about these days. And if you take that increase in precision, which is more or less indicated in that blue shaded region in the plot on the left, you see that the value of the Hubble constant from these more or less local methods based on the distance ladder and then supernovae has more or less given values around 70 to 75 kilometers per second per megaparsec. And it hasn't really drifted, but the errors have shrunk to a level now of order 1% or maybe 2%. But if you look at the cosmic microwave background measurement, which is shown in red, you see that even though they agreed in the area of W map, the moment that Planck came along, you see a sudden decrease in the value of H0. And this is largely to do with the much better way that Planck is able to deal with systematics, such as foreground removal, polarization, etc. So Planck came with a much lower or significantly lower value of the Hubble constant. And suddenly you see that these two methods diverge. They don't agree anymore, right? The error bars, even at 2 or 3 sigma level, do not overlap. And this is not just true for the cosmic microwave background. This is also true if you look at baryonic acoustic oscillations. They agree with CMB measurements. They have more or less the same underlying physics. They measure things at different redshifts, but it's the same physics that drives both. So in general, BAO and CMB are bunched together and combined, and they agree with each other, and they are called early universe methods, and late universe measurements are the distance ladder, the supernovae, and also gravitational lensing, as I will show in a moment. So this is just a summary of that tension. If you bunch them together in early and late universe, again, you see that if you have just CMB with or without BAO or any combination, you find values in the upper 60s, whereas in late universe measurements, which are based on distance ladders, supernovae, you find values that are close to 73 with very, very small errors. So this is really, right, what the tension is all about. So is there another, right, this tension is developing, and now you can ask, well, is there another method? The distance ladder itself, of course, it's not called a ladder for nothing, right? There are various stages in such a approach where things can, right, go wrong, the systematics, right, and they might add up. So is there another method in the nearby universe that is fully independent of these methods and can measure, right, the expansion rate of the universe in hopefully one step? And of course, strong gravitational lensing is such a method. Now, you've all seen strong lenses. Maybe tonight when you're watching the football game, you might be drinking a glass of wine, and you might look at a candle, although the temperature might be too warm for that. But if you look through the bottom of your wine glass, you might see multiple images of that candle light. Right, for example, in the upper right, you see 3 or 4 images appear, or 2 images. In the bottom right, bottom left, you see a ring, all distortions of that background candle. Now, gravitational lenses are very similar. It is to first order geometric optics, where a background source is distorted by the gravitational potential, right, under Einstein's theory of general relativity, right? Space and time are curved. So this galaxy with its dark matter halo will act like a geometric lens. And that is basically, right, gravitational lensing 101. Now, it's not just that the images are distorted, the light from various parts in that image also arrive at various different times, because they traverse a different path, but they also traverse through a deeper part of the potential. So there's both a geometric and a potential time delay. So the parts of those images that you see are not arriving at the observer at us at the same time, but there will be delays introduced by the effect of gravitational lensing. And it's those delays that we use to measure the size of the universe and thereby the Hubble constant. Right? So, but we don't use this type of lens that is shown here, but we use lenses with quasars in them. Quasars are variable, and because they are variable, you can measure the light travel times or the differences in light travel times, as I will show in a moment. So this is an example of one of the lenses that are being used in the Holy Cow project, from which we have measured the Hubble constant, for example. So you see a central galaxy here, and you see 4 quasar images around it, 3 on the left, 1 on the right. And by measuring the brightness fluctuations of those images, we can measure time delays. Now, very simply said, and that is shown here, right? What we do is we look at the quasar on the left. It's varying in brightness. It sends out photons. They arrive at different times at the observer, again, because they traverse different paths and go through different parts of the potential. And that time delay is then a measure of the size of the universe. So the larger the universe, let's say on the top, you have a larger universe than on the bottom image here with the galaxy, right? So the larger the universe, the larger the time delay, and the smaller the Hubble constant is. That's, again, the very basics of time delay cosmology. Now, it's a little bit more complicated than that. And I'm not sure if you see my mouse, but maybe you do, right? You see this combination of Ds here, dl, ds, dls. So these are angular diameter distances, and these fold in also the cosmological parameters. But to first order, this here is inverse proportional to the Hubble constant, right? So, and therefore gives us, if we measure a time delay, right, we measure what the mass distribution of the lens is, we can measure this Hubble constant up to some modulation depending on the cosmological parameters. Now, it turns out that in strong lensing, this dependence on cosmological parameters is rather weak. So that makes it a very powerful method to directly infer H0 without having too much degeneracies in the models. Now, I've been doing this for the last 25 years. This was actually the reason why I was hired as a PhD student a long, long time ago. And in those days, we were dealing with very large errors on time delays. In fact, when I started my PhD, no time delay had ever been measured between lensed images. We had very simple models for the mass. We had very simple models for everything else in the field along the line of sight, just an external shear. So the models were very crude and the measurements were very imprecise. At the moment, we have very, very precise measurements of time delays. We have very powerful models and methods to model these systems based on HST and adaptive optics images. We're using stellar kinematics. We're modeling the entire environment of the lens and also along the line of sight. So there have been dramatic improvements in the modeling and in the data quality of these systems, such that we can now measure H0 to levels that are competitive with that 1 or 2% measurement in, for example, from supernovae or distance ladders. So the results that I'll show are based on two projects: the Holy Cow project, which is a project that does the imaging, the spectroscopic data of these lenses, does the modeling, and also the Cosmogral project, which is actually monitoring these quasars for time delay. So these two programs joined forces in what we now call the TD Cosmo program, and of course, because both are needed to measure the Hubble constant. You need the time delays, but you also need accurate mass models. So this is the current sample of lenses that we are investigating, these 6 here, but there's actually a 7th one, which I will show results of as well. These are all quasar, 4-image quasar lenses. Actually, the one of them in the bottom left is a double, and all the time delays between these images have been measured. The mass models have been determined, line of sight, etc. So we have all the ingredients necessary to infer the values of the Hubble constant from each of these systems. So first of all, right, we need a time delay measurement, right? Without it, we can't measure the size of the universe. So how do we do that? So for this, there are very long-term monitoring programs on sort of small-scale telescopes, 1-2 meter telescopes around the world. You need those light curves almost continuously. And then a beautiful example is shown here for one of the lens systems. And if you zoom in on these light curves, just to make it a little bit more clear, right? These run sometimes over a decade. But if you zoom in on a smaller part here, you can see the 4 quasar images vary, and you see, for example, that there is a delay. If you look at image B, for example, you see the same as in image A1 or A2. There are some modulations between them due to microlensing. I will not go into that, but you clearly see that this light of image B arrives before that of image A1 and A2. And that image C arrives again a little bit later. So this is how you measure the time delays, of course, with the caveat of microlensing that can be statistically folded in. The other ingredients in the model, in this equation that I showed earlier, are the mass model of the lens and nearby companions. They are correlated, so we treat them in a similar fashion. Nearby companions can contribute also, for example, to the dynamics, for example, in the form of a joint halo. So again, the data quality has dramatically improved over the past decades, going from ground-based seeing limited images on the top left to Hubble Space Telescope images in the middle, and currently we're also using Keck adaptive optics images on the bottom right with about 60 milliarcsecond spatial resolution. So the data quality has dramatically increased, and therefore also the information that we have about the mass distribution in these lenses. You see those arcs here, and all of these distortions, the information in there can be used to reconstruct the mass distribution of the lens galaxy. So that information is used. Now, in addition to that, we also obtain stellar kinematics of the central galaxy, and that we combine with the gravitational lensing information in the arcs and build a self-consistent model that can also break some of the degeneracies, such as the mass sheet degeneracy. So that's again a very powerful piece of information that we're currently adding to the models. We're modeling the surrounding fields. Now this is a particular a complex example here where the galaxy is part of a more denser group. So all of these group members are modeled in various ways, and all of those uncertainties also between model families are folded in a fully Bayesian way in the final analysis. So just to say, right, this is a fully Bayesian analysis that we do, and we take all the uncertainties and propagate them through our models, including if we choose various different model families with different parameters, we're also combining those into the uncertainty budget. So this is trying to cover as much of the degeneracies and uncertainties as we can. Now, we developed over the past decades grid-based modeling techniques to model these extended lensed images. If you subtract the quasars, in this case, this is observed data. This, for example, is the model of the extended images. This is the same one with the quasars included. And then this is the source here. So we can model this data down to the noise level and use all the information there is. And then finally, the most uncertain part, up to recently at least, is the effects of the line of sight, right? Not every line of sight has the average density of the universe. Sometimes it's overdense, sometimes underdense. We use several methods to quantify that, either by counting galaxies in the surrounding field. So we can, and then compare that, for example, to other observations or to simulations, and then make a probability distribution of the extra, what we call convergence, the extra surface density added on top of the average density of the universe, or it could be an underdensity as well. And those probability distributions are shown here. So these errors, these uncertainties are folded into the modeling. So this just adds an extra error into the budget. And we compare it also to weak lensing measurements around these, and we find that they are consistent with each other. So galaxy counts and weak lensing agree. So we're pretty confident that we are doing the right thing in folding in the line of sight contribution to these lenses. So what are the results? So let me immediately go in there. So what I will show now have all these ingredients for 6 lenses or 7 lenses actually. And the results I will show is under the assumption of the standard flat lambda CDM universe. So if we do that, before I actually show you the results, I have to say that we do all of this analysis blindly. Except for the first lens, which was analyzed a long time ago, all the other 6 lenses, we infer a value of the Hubble constant without anybody in the collaboration knowing what its value is, until we unblind it. And we have written the paper at that moment already. That value then goes straight into the paper and is combined with other values and is published as is. There's no modification at that point. And we've done that for all last 6 lenses. So just to make clear that this is not, there's not some confirmation bias in this program. So this is the result of the first lens. Again, for full disclosure, this is the one that was not blind because it was analyzed more than a decade ago. But the next lens is done blindly, and the value was somewhat higher. And the black curve is the combination of the two. Then the next one, the next one, the next one, and the next one. So this is now what we published, actually the reference below, that's already a bit out of date, but we published this now in a paper, 6 lenses, fully blindly, except for the first one, analyzed with a Hubble constant value of 73.3 plus minus about 1.7, 1.8. And that is clearly, again, much larger, significantly larger than that of CMB and BAO. So also from lensing, we find that tension persists. Now we've added a 7th lens from a different program, but analyzed in a very similar fashion. And again, this lens here, oops, if you go here, right, is in full agreement with the other lenses. And if you combine it, you get an even sharper measurement of the Hubble constant value. So this is where we are in this program. We have, under the assumption of the flat lambda CDM, the lensing results. So on the right, you see the 6 lenses from Wong et al., and then adding the 7th lens, right? The tension persists. It's fully consistent with Hughes, which is the supernovae measurement of the Hubble constant. And on the left, you see the measurements from the BAO and from the CMB. So again, there is quite significant tension at the 5.7 sigma level. So the tension persists. It's not just supernova distance ladder, it's also gravitational lensing that disagrees with the CMB and BAO measurements. And we regard gravitational lensing more or less the same redshift range as Hughes, right, to be a late universe measurement. So can this, that's the last thing I will discuss, can this tension be alleviated? Now, right, under the assumption of the flat lambda CDM, this is now turning out to be very difficult, and we are working extremely hard, of course, to figure out whether we have systematics that we haven't thought about, and we're actually writing several papers on that. But again, the conclusion is our answer doesn't really significantly change. Now, of course, the BAO and also the CMB teams doing the same, coming to the same conclusion. They cannot find anything obvious that would lead to an agreement within the context of flat lambda CDM. So, right, what is necessary? So probably if it turns out, right, there are no hidden systematics, we need to modify the flat lambda CDM universe. And of course, people have written many papers on this. People are changing the equation of state of dark energy. People are changing the number of relativistic species. People are even considering the universe not being flat, right? There to be modifications of dark matter, maybe some dark matter self-interaction, annihilation, and even early universe dark energy. If you look at these, then they can all shift mostly, actually, the early universe measurements in the direction of the late universe measurements. So that's shown here. But none of them by themselves is really sufficient to bridge that now already 5.7 sigma gap. So maybe a combination is needed, or something else is needed. But right, something needs to break down in lambda CDM if we believe these measurements are both, right, relatively free of systematics, and the precision now is good enough. So we tested this also with lensing. We have gone through a very long list of alternatives to the flat lambda CDM. So these are all of the models that we have tested, also with various priors and other assumptions, which I will not go into. I will just show a few examples of what happens, for example, if you have an open universe on the left, right? In that case, also for Planck, you see that if you let the flat universe go, that actually your answer gets worse, right? So in fact, Planck prefers a universe that's not flat, right? And we've seen papers appear on that, and only by forcing it to be flat do you actually agree a little bit with lensing measurements. So actually making the universe open makes the tension in some sense worse. It drifts away. You can also nicely see that the Hubble constant from lensing is very weakly dependent on the curvature, on the flatness or the curvature of the universe. You can change the equation of state, and similarly, right, you can right, you cannot really get them in agreement. It gets a little bit better, right, but it's certainly not a full solution. You can also play with evolving dark energy equation of state, and again, right, you can improve things a little bit, as I shown in a couple of slides ago, but it's not a full overlap between them. And then finally, you can also play with the number of relativistic particles. And again, if you do that, things might get a little bit better, right? If you increase the number of relativistic particles, things seem to start drifting to a higher value of the Hubble constant. So in agreement with lensing, which is not dependent on the number of relativistic particles at all. And if you deal with the mass of the neutrino, then things really don't help that much either. It's along this line, so it's not going in the direction of where it should go to alleviate the tension. So the mass of the neutrino doesn't seem to be part of a solution here. And of course, you can also combine them simultaneously, but one comes up with more or less the same answer, that changing the number of relativistic particles or the mass of the neutrino can alleviate a little bit, but not entirely. So that brings me to my last slide, right? That's also my summary, or my one before last slide, is that it's currently clear that there is a persistent tension between the CMB and BAO, not BOA, BAO, and local universe measurements of H0, including, as I've shown, strong lensing, if a flat lambda CDM universe is assumed. And as I've shown as well, if we believe that, right, we have measurement systematics in the astrophysics, let's say, under control, then alleviating this tension probably requires new physics, maybe, right, letting go of the flat lambda CDM universe. And so I'd like to thank you all, and I would like to also wish you tonight great enjoyment with the Coppa Italia. Thank you very much.